So before we move on, I want to take a look at a little variation of the Königsberg bridge problem. And it's going to start off with a new definition here. Now, if you read through this, you'll see that it's very close to our definition of an Euler or an Eulerian circuit. It still has the requirement that we have to pass through every vertex at least once and every edge exactly once, but I've removed the requirement that we start and stop at the same place, right? And instead, I've replaced it with this requirement here that we just have a predefined starting and ending vertices, and that it's okay for them to be different, right? So it kind of, again, in the context of that Königsberg bridge problem, now we want to cross every bridge exactly once, and we want to start at our house and say we want to end at our friend's house instead of starting back where we started. Okay, so there's a very simple rule that we can use to determine whether or not this so-called Eulerian trail exists. And it's very similar to the one we saw for talking about Eulerian circuits. Again, we're looking at the degree of the edges. And what we're going to require now is every vertex has to be even. The degree of every vertex has to be even, except for the starting and ending vertices. Those two have to be odd. Right? Under those requirements, then we will have this Eulerian trail. Okay, the proof of this is very similar to what we did with the proof of our method for finding an Eulerian circuit. So I'm going to set this one aside and leave this. If you're following along in the online classroom, it'll be one of the exercises there. So we've got some examples for us to look at here. The big graph on the left with all the circles in it, that one does not have an Eulerian trail. Vertex 1 up there in the upper left is isolated, so the graph itself is disconnected, and that's the very first requirement. The graph has to be connected to have an Eulerian trail or an Eulerian circuit. The graph in the upper middle, that one does have this kind of trail. Vertex 1 and 3, they both are degree 2, that's even. Vertices 2 and 4, they both have degree 3, which is odd. So there is an Eulerian trail here, and it's going to have to start at either 2 or 4 and end at the other one. It's pretty easy to see what this is going to look like. The trail would start, if we start at 2, it's going to go to 1, then down to 4, down to 3, over to 2, and now we've touched every vertex, which is good, but we haven't touched every edge. So from here, I still have to cross E5, and that will take us to V4. So we started at V2, we ended at V4, and that's exactly what we expected to happen, since those were the two with the odd degree. So the end result here, if we lay out the vertices, right, 2 to 1 to 4 to 3 to 2 to 4, the vertices, some of them repeat, and that's okay. Our only requirement with the vertices is that we had to touch them at least once. More than once is fine. Technically, yeah, usually we put the edges in there as well. But at every step here, there was only one way to get from the starting vertex to the ending vertex. So the path should be clear even without those edges specified. Now the third one, in the bottom right, that one does not have an Euler trail. All of the vertices, their degrees are even. 1, 3, 4, and 5, they're degree 2. Vertex 2 is degree 4. So we do not have the required 2 vertices to have an Euler trail. The graph does have an Euler circuit because all the vertices, their degrees are all even, right? But no trail. So yeah, the two are mutually exclusive. Right? You can't have one of them and the other. So far, we've been very focused on the edges in our graphs. Right? Our strictest condition has always been that we're only allowed to touch each edge one time. Now, in the next lecture, we're going to turn that around and think about paths or circuits through a graph that have similar restrictions, but instead, it's going to be on the vertices. So you can find a link to that next lecture below. And of course, if you like this lecture, please don't forget to click on the like button down there as well.